Thank you, everyone. Maybe a little bit about what we do and who we are right quick before I get into the facts or fiction, because the biggest question I've got at the conference is I don't think anybody knows who we are. Strangeworks is a quantum computing software company based in Austin, Texas, and we are focused on what we call exotic compute or non-traditional compute, so not just quantum, but other flavors of morphic, neuromorphic, DNA-based, things like the Grok processor, and making them all work together as efficiently as possible so that you can not focus on the software or hardware and focus on your research capabilities and actually finding solutions with these amazing tools. Today's talk is going to be a not technical talk, because I think the more conferences we go to, the more we learn that as an industry, we are speaking over the heads of the people we are trying to get to adopt our products. And so we wanted to talk to the facts and the fictions around quantum computing. Quantum computing, as we all know, is very hyped. It is probably still got a little more to go on the hype cycle, and there's probably some time before we'll have that noise kind of worked out of the system. I do believe that this will happen in the next year or so. I think we're starting to see that trend already. If you watch quantum Twitter, there are many people who are calling out other people if they say something that's not factual. There's a lot of people sharing data more openly to get to facts and standards and consensus on opinions on the computers and the qubits and the machines and how they work together. So that's kind of going to be the focus of the talk. But I wanted to make sure that I might say some of these words. And if you look in your swag bag, our contribution was a buzzword bingo card. And so if you see this card is on English in the front, it's on Japanese in the back. And this is not for my talk, this is for the entire conference. If you hear a word like quantum supremacy or fault tolerance, optimization, I'm sure has already been said, and I'll say it, and you mark it, and you get bingo, then you can find myself or Steve Gibson or Andrew, and if you don't know what we look like, on the bottom of the card we put some little pictures there. So we're very easy to find, and I'll hand that to Steve. And so feel free to play that game, and we do have some prizes for you. We have not said what they are, but they're custom merchandise from Strangeworks. So hopefully some of you will win, and we would love to give that to you. So let's get started. Again, the focus is on quantum computing, fact or fiction. I have spoken to over 300 enterprises worldwide, and I get the same questions all the time. Does the number of qubits matter? When will it arrive? How useful is it? You know, I read a thing that somebody achieved quantum supremacy or quantum advantage. Is that true? How can it be validated? How can you benchmark? Tons and tons of questions. And so what we wanted to do is just kind of talk about our view of how we view the industry in the context of the questions we get asked and what we think are the factual, unbiased answers. So let's start with the fiction. Let's start with fiction because just last night, as we were preparing for this morning, there was a Twitter storm where a quantum company had posted something, and some of our fellow constituents had called them out publicly, which is something I've been seeing more and more lately. And it was around their technology and the claim, and this is going to be common. But if, as an industry, we can't be truthful and sincere in everything we do, how do we expect any customers to spend their money with us and adopt our technology so that we can actually build and grow the industry, right? We can't. That's not possible. And so the first one that we hear all the time is that superposition, quantum superposition, represents a 1 or a 0 or everything in between, right? And you know, I always use this simple coin example. If this white side of the coin is heads and this blue side is tails, if I put it in the palm of my hand, heads up, it's a 1, tails up, it's a 0. But if I put that coin in the air and flip it, at the top of that spin, it's in a quantum superposition of a 1 or a 0, a probabilistic set, not everything in between. And so there's some probability. And much like Schrodinger's cat, when I flip the coin and I catch it, until I stop it and I measure it, then we don't know what it is. When I measure it, the system collapses. I know that this is a tails. So that's one of the ones we hear very, 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 very often. The other one I already mentioned, which is, does the number of qubits matter in a machine? And the answer is no. Some machines have 5,000 qubits, some machines have 50 qubits, some machines have 12 qubits. Is it a photonic system? Maybe it's an annealer or superconducting circuit, some other form. This is all relevant to judging these machines, and there is no really good standard benchmarking either within an architecture of machines or across machines. And so this is really important because customers have been having their buying decisions influenced on the number of qubits and not what they can actually do with the machines. We are very early. There is not a huge market. There is not a lot of people spending a lot of money. When I see some of the research reports, I call them into question. The BCG research report earlier today was fantastic, and I think they're one of the best. There's a lot of others. I think maybe they overinflate the activity in the market. But when a customer is making a decision, they think classically. They think, oh, this processor is faster than that processor because it has more transistors, and they can't apply that to quantum, and it's wrong to try to apply that to quantum in our marketing and our messaging to these customers. We want people to be successful with these machines. I want to see the world changed dramatically in environmental sciences, and I don't want drug discovery. I want the elimination of disease. I don't want a better battery technology. I want completely new forms of travel and innovation. To do that, it requires us to be sincere and honest when we're talking about the capabilities of machines, and that includes in our marketing and messaging. The other thing is, very simple and self-explanatory. Quantum computers do not try all solutions at one time. That's not how it works. I won't go too much into depth in that one because I think that one, again, is very, very understood. Similar to that, a lot of people say, that quantum teleportation allows for time travel. This sounds funny to all of us here, but if you have no idea of quantum and you read this in a reputable magazine, say the New York Times or Time magazine or something, this is something you might believe, right? That we know not to be true. And so that's not on the reporters, that's not their responsibility. It's on our responsibility to educate not just our community, but everyone about what these machines do, why they're valuable, why all of us are so very excited to be using them. Similar to that, I read an article recently that said that quantum computers can predict the future. If it would, I would buy one today, right? But I don't think that it can. It doesn't, it sounds so crazy for some of the people in this room that work with this technology every day. But I always tell people, if you step outside of this room, if you go to Tokyo Station and you ask 200 people about quantum computing, they have no idea what you're talking about. And so again, if someone reputable takes some information and mistranslates it, misinterprets it, then we have these situations where people start thinking about worries. And why is this dangerous? This is dangerous not only because of the expectations of investors and other parts of the community, but it's especially dangerous when we start thinking that quantum computing will be one of the most regulated fields by government ever. I'll talk about cryptography and things like that later. But because of the power of these machines, governments will start regulating them. Some governments already are. And so if you go to a bureaucrat in the US, the Congress, they don't understand Facebook or Twitter. What are they going to do if they think quantum computers predict the future or can tell you everything, right? That's going to affect the way they write regulations. It's a very dangerous thing for us as an industry. Quantum computing cannot mine cryptographic transactions faster. The cryptocurrencies, this is a question every single person, we get questioned on our website, we get this question everywhere. Different function, different math. I know there's people working on this, but that's really, really important to understand. And of course, quantum computing is production ready. It is not, and that's okay. As a software engineer, I look at quantum computers less as production machines and more as really, really good lab equipment for exploring the quantum landscape. The reason I say that is because 4 years ago, when we started our company, we used to make the joke that we write software for computers that don't exist. And now they've come a long way. When we started, 12 qubits, 17 qubits. Now, IBM has 127, a path to 433 in the very near future. Things are clearly advancing faster. But these things are not resilient. They don't stay operational for as long as we need. Sometimes the circuit time, the algorithm we're running, is longer than the decoherence time of the machine, right? These are things that have to be solved before we can say these things are production ready. That doesn't mean I'm not the most excited person in the room about quantum computing. That doesn't mean you shouldn't be investing in it. It just means we have to be realistic about where we're actually at and where we're going and the timelines with which we're doing that. So my favorite is quantum computers are going to replace classical computers. I still hear this. I heard it before I even started the company, and I hear this all the time. And the fact is that classical computers and quantum computers will be working in concert along with many other forms of computers, not just annealing technologies working with superconducting, working with classical, but amorphic, neuromorphic, DNA-based computers in the future, plant-based computers, all kind of things that we can't even imagine that I believe quantum computers will help us unlock the paths to. And so when you think about it, Shor's algorithm is a great example. You have 5 steps. Only one of them needs a quantum computer. It would be a waste of the time and money and resource to try to do all 5. I could write an iPhone app that could do that. So each one of these problems has unique areas where these technologies can be applied, and we need to be very, very aware of that. So the last one, I believe, is quantum computers will be the end of security. I'm sure we've all seen tons of articles about once a quantum computer is working, everybody's encryption will break. But that's not how encryption works at all. Security is an ever-entwining dance of threat and remediation. You build a wall, I tear it down. You build a higher wall, so on and so forth. And so what would really happen is in this situation is if I had a quantum computer right now today that could break an RSA key, I would break Steve's key. And then I would have to reset everything, and I would break Andrew's key. And the real threat to this is more for things that would be steal it and save it, where government secrets, industry secrets have been stolen that are encrypted with lesser technologies. Those will fall. And quantum computing eventually will break all of the encryption. But guess what? We'll have post-quantum algorithms, we'll have post-quantum cryptography. These will be just the way it works. There used to be in many of the world wars encryption that people thought would last forever. And nobody has used that in 50 years, 60 years, 70 years, because it changes over time. And so things like the quantum internet, quantum sensors, quantum computing will help build new and safer forms of security. And the last one is you need a PhD to operate a quantum computer. You need a PhD to build a quantum computer? Yes, but we already have enough abstraction layers from our community, which makes me very happy that there were 4 university programs with master's degrees in quantum information science when we started the company, and now 4 years later, there are 37. And part of the reason is a bunch of the wonderful people that are sponsoring this conference, that are exhibiting in the halls, our company, have created abstraction layers to make it easier and easier for people to access these machines. So now for the facts. And I'm going to rocket through these, but we'll get through so we can end right on time. The first one is, it's the biggest revolution in computing ever, right? I believe this. This is why I got into quantum computing. I believe that by the end of this decade, by 2030, quantum computing will have changed the course of computing more in this 10 years than it has in the history of computing. I think that it is very important not to focus on applying quantum computers to the problems of today, but to use quantum computers to unlock the secrets of tomorrow. I don't look at quantum computing as making the financial transaction faster, or the better battery, like I said, or a better drug. I look at it eliminating disease. I look at it coming up with completely new forms of travel. This is what we should be using these machines for. So next, quantum information is very sensitive. We know this. It's very sensitive to electromagnetic interference, through gamma rays, through all kind of things depending on the machines. And different machines have different resiliency to this information, but it's still very, very sensitive. We don't have quantum RAM, for example. It doesn't work like a normal computer, right? It's a very specialized device, very important device, but still very specialized. And that information is very sensitive, and there are a lot of people working on solving these issues. Some algorithms solve problems faster. John Preskill and his team published a paper in December that I really liked that showed that they could do experiments much faster than a classical computer using about 40 qubits. They ran about 1,300 experiments. Very impressive. I suggest everybody check that out if you haven't already. I think it's a really good example of a true quantum advantage. I think it's one of the first examples. I think it's one of the first of many. It doesn't matter who finds quantum advantage first. It matters that we find quantum advantage in every single area we can and apply it to the problems that we're facing. Entanglement, primary resource of quantum. It's very, very valuable. It's not just for quantum computing, but for the quantum internet at large. I'm a very big fan of quantum internet projects. Recently, there was an experiment that went 127 miles, entangling 2 qubits to send information over. I like it because of everybody's fear of security. If you have an entanglement as the principle for the network, and we were to observe it, then obviously it would break and you wouldn't get my information. So this is very, very exciting to me, not just in the computing side, but in the internet side as well. Another fact, qubits can store an exponential, if you had a amount of bits, everybody doesn't think this, 4 bits, 16 outcomes, you can be in any one at the same time. If you have 4 qubits, you can be in all 16 at once. And if you had an infinite precision with your qubit, a single qubit could encode the entirety of Wikipedia, right? So very, very fascinating. These things are extremely powerful. The other quantum could crack common encryption. That's going to happen. We need to just accept this as fact, and then we need to plan for it strategically with how we're securing data, how we're improving with post-quantum cryptography, et cetera, et cetera. This is very important. It was 1994 when Peter Shor came up with Shor's algorithm. The ideas he had there about the implications of quantum on security are going to be realized before the end of this decade, without a doubt. And then there's an exponential advantage for new chemical design. This is something we're already seeing with our customers. You clearly can do it. Think about it. If you wanted to model a molecule, like a caffeine molecule, we've probably all had some caffeine this morning, it would take an enormous amount of memory. But you could do the same thing in about 160, 170 qubits, and that could fit on a chip the size of my fingernail, right? So this is a very, very big thing. There's going to be a lot of movement in chemistry, I believe, and material sciences as one of the early movers we see taking advantage of quantum computers. Quantum internet, I've talked about a lot. I love it. I'm very excited because it could be used not just to secure data, but to exchange quantum data. This is fascinating. If you think about the evolution of computers through time, one of the things that gets me excited is that with classical computers, let's go back to 1958 and a guy named Jack Kilby who invented a thing called the integrated circuit. And right around 1963, it had become adopted enough that it was being integrated with products globally. I believe that 2023 will be 1963, and that's a big starting gun for our industry. But I also believe that because of this ability to exchange quantum data and everything, you're not going to have the same trajectory that we had over years and years and years to get to where we are with computing technology today. Because we can use quantum computers and quantum data exchange to solve problems with quantum computers, to create new forms of the materials we need, the physics we need to discover new things. So I think quantum computing you're going to see have a much, much faster rate of growth and a much, much higher rate of impact. Quantum computers are not scalable yet. There are a lot of people who want to tell you they are, but this is true. They're not. It's very, very hard. What these hardware companies are working on is not easy, and I applaud them for their efforts. It's incredibly difficult. And will we get to scale before the end of the decade? I think in a couple of architectures we will. Are we at scale now? No, and the reason is there's a difference between advanced research and applied research. And advanced research, we're doing the research, trying to solve the problems, doing everything. Somewhere on the applied research side, we move from physicists building and designing the machines to electrical engineers cranking them out and making the scale and making the capacity. We're somewhere in between those two right now. Kind of the uncanny valley, if you will, if you know the robotics concept. It's very similar to where I believe this industry is. And development will require new practices. This is 100% true. In 2008, I worked at a software company called BMC Software, and we were part of the group that came up with what was called DevOps. And we had to come up with new ways, new processes of developing software, because now software was really taking off. You think of the Facebooks coming out, the Instagrams, and all of these other things. Software developers needed new tools. IT departments needed to be able to relate and organize things with those new tools. We're going to need some form of science operations, or as we call it, PsyOps. This is very important that we have new practices for these new machines. It doesn't mean it changes everything. We don't rip down what we do. It should integrate the way we already work, right? The way we already work should be integrated with all of these new technologies, not making people change what they're doing to adopt the new technology and have a completely new workflow or process. This makes no sense at all. Enterprises have invested millions of dollars into that. So at last, I'll be here for the rest of the conference. I would love for you to tell me what you've heard so that I can add to these slides, so I can add more data. And with that, I will thank you for your time and have a wonderful time at the conference. Thank you very much.